Hello. In this video I would like to go over Lewis symbols, or also called Lewis dot structures, which is a way to represent the valence electrons or the valence shell of an atom or an ion with dots placed around the center or the letter symbol of the element. And this was conceived by the American chemist Gilbert Lewis about 100 years ago. And so this is a very simple but and not exactly accurate technique to indicate how atoms and electrons how atoms share electrons when they bond, but it fits the trends in the periodic table very nicely and therefore is used very commonly. So first of all, here's an example of how Lewis symbols or Lewis dot symbols are used for third period elements right here. So we can see, for example, sodium has an s1 electron, so it has one valence electron, so we indicate that with a dot right here next to the symbol for the element. And then for magnesium we write it with two dots, and we write one dot each element or each electron as one dot by itself in some kind of square arrangement around the symbol until we end up with 4 dots, and then we start pairing up these dots until we end up with 8 dots around the element. And usually the elements that are in the main group tend to form reactions that leave them with 8 outermost electrons. So 8, and these are 8 valence electrons. And we call this the octet rule. So that's something worth noting here. So elements or many main group elements, so this is the octet rule. The octet rule states that elements in the main group tend to undergo reactions where they share electrons with other elements such that they are left with 8 outermost electrons. And this is a 10. There's a lot of exceptions right here. It's a rule, it's not a law. So tend to undergo reactions that leave them with 8 electrons in their valence shell. And there are a lot of exceptions to this rule, so it's not too important to get too hung up on this. So certain one, a very important one, is hydrogen. Hydrogen will only react with one other electron to form a duet, or 2 electrons to fill its valence shell. So we'll see that in more detail once we see the electron configurations of different elements in more closely. But for our practical purposes, when we see elements such as carbon, nitrogen, oxygen, which are the ones that we're generally interested in for the for much chemistry that involves living systems, and also polymers and plastics and many manufactured goods, much of the chemistry is done with the elements carbon, nitrogen, oxygen, fluorine, some of the halogens, maybe silicon, and so on and so forth. And so for those elements, we end up with 8 outermost electrons. So we can basically then write that these elements right here end up forming a certain number of bonds, which we can also list right here. So we can also list that so the noble gases right here, they do not form any kind of chemistry. So they do, and so they're chemically inert, and the halogens tend to form bonds that, so they form usually one bond with something else, so one bond. And oxygen will form 2 bonds, or a double bond. Nitrogen will form 3, carbon 4. And now the rule is its boron will not form 5. Boron will only form 3 because it is very small. Boron only has 3 valence electrons, so it ends up forming 3 bonds. So that's another violation of the octet rule. So it's important to take that octet rule with a grain of salt. And hydrogen will tend to form 1 bond as well. So let's see how that works. So then we can also look at this as the number of valence electrons. So as we indicated in the previous slide, each main group element will strive to form 8 valence or achieve 8 valence electrons to fill its valence shell. So lithium has 1 valence electron. So lithium has 1 valence electron, beryllium has 2 valence electrons. So these group 2 elements have 2 valence electrons. These group 1 elements have 1 valence electron. Then we ignore for now the transition group elements, and these would then have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. And like we see, as I mentioned, the elements tend to undergo these reactions so that they share electrons with another element that they do a reaction with that leave them with 8 valence electrons or 8 shared electrons somehow, so that their valence shell is filled. So let's look at an example right here of oxygen. So if we have oxygen, the molecule O2, and we can see that oxygen, we can write it the Lewis dot structure for an oxygen atom, like so, where we have 2 paired electrons and 2 lone paired electrons. Again, we always fill in the electrons in a square around the atom, and once we start filling each square with 1 electron, and once we fill all 4 squares around the atom with an electron, then we can start pairing them up. And so we can then get another oxygen atom, since we're looking at so oxygen ends up with sharing this pair of electrons right here and forms 1 bond right here. And now this can now be a bonding pair of electrons. And so we can see that now oxygen has at least 1 pair of electrons bonded with each other. And then we can also see that there are still 2 lone pairs or 2 lone electrons that would like to get paired up, because each oxygen at this point right here still does not have a complete octet. So we can then bring these other 2 electrons into the bonding region. So this one right here, we can bring that into the bonding region, and this one right here into the bonding region, and make it a double bond. That's what it's called, a double bond, where we have basically 2 pairs of electrons in the bond, and then 2 lone pairs of electrons in each bond. So oxygen then, therefore, each oxygen atom, we can think about this as a Venn diagram right here. So each oxygen atom has 8 electrons now around its orbit. So it basically, we can count the shared electrons. So it has, this oxygen atom is now surrounded by 8 electrons, the shared electrons from the bond and the lone pair electrons. So it has 8 electrons, and the other one does as well. So we can think about this one right here. It has a shared electron pair, and so each oxygen now has satisfied the octet rule. The oxygens are sharing 4 electrons amongst themselves, so that way each one of them has a complete octet and satisfied that octet rule. And so we can also indicate that double bond right here with a line. So we can also write this as 1 single bond, like right here. We can indicate that with a line. So each end of the line we can think of as an electron. And so the electron pair right here we can write as a line. In this case we have a double bond, and then we can write the lone electron pairs on the side. So this would be the arrangement for the oxygen molecule. For nitrogen, well, let's actually try hydrogen. Hydrogen has one valence electron, And so hydrogen has the formula H2. And in this case, hydrogen only needs one more electron because it has only the 1s orbital, and the 1s orbital is filled with 2 electrons, so it obtains that noble gas configuration with just 2 electrons. So it really only needs to share an electron with something else to complete its noble gas configuration. So in this case right here, where it can share these 2 electrons, can be shared as one bond, and we end up with H2. And then therefore we can see that if we look at a Venn diagram right here, so this hydrogen right here has 2 electrons in its influence that is shared with the other hydrogen, and likewise the hydrogen atom on the right has 2 electrons in its influence, but both of those electrons are shared in that bond. So let's think about if we can do the nitrogen molecule. Let's take a moment and think about it, and pause the video and see if you can do this on your own. Okay, so the nitrogen molecule would start off by drawing the nitrogen atoms. Nitrogen has 5 valence electrons, so 1, 2, and then we draw the remaining electrons as single electrons. And again, we can make a bonding pair out of the 1 single electron right here, so we can make this a bonding pair right here. But now we see that we have these other 2 lone electrons right here, so we can also, like we did before, bring these into the bonding region, and that way each nitrogen has 8 electrons that it has and it's sharing with the other electrons, so with the other nitrogen atom. So we draw it like so, then we can see that nitrogen and then we have the lone pair electrons right here, and so we see now that each nitrogen right here has 8 electrons under its completes its octet with 8 electrons right here. 6 of them are shared with the adjacent nitrogen, and then likewise the other nitrogen also has 6 electrons, but 8 electrons, but 6 of them are shared with the adjacent nitrogen. So each of them now has 6 electrons around itself, so 8 electrons around itself, so therefore the octet is complete. Let's make a slightly more interesting. Now look at a polyatomic molecule. So let's look at something like methane, CH4. Let's try and do that with CH4. And carbon, like we saw earlier, has 4 valence electrons, and hydrogen has 1 valence electron. And so each hydrogen can come in and share 1 valence electrons with the carbon right here, and it then therefore is sharing the. So then that way carbon has a complete octet, and hydrogen has its complete duet or pair of electrons that it requires to get to its noble gas core. So we can think about each one of these becoming a bonding pair. And so we can easily represent this with lines. And again, now in this case right here, we can see that if we draw the Venn diagram here, carbon here has 8 electrons in its orbit, so or under its influence. 4 of those are shared with 4 of those originally come from the hydrogen. 4 of those come from the carbon, but because they're now shared with the hydrogen, this brings stability and it completes the octet. Hydrogen likewise, now each hydrogen has 2 electrons under its influence, so that are shared with carbon, and therefore the compound is stable. Let's see if you can come up with the Lewis dot structure for water, H2O. Take a moment and pause the video and see if you can figure this out on your own. So with water here, we can, oxygen again has 6 valence electrons, and hydrogen has 1. And so we can just complete the octet for oxygen right here by making a bond between the hydrogen and the oxygen, and that completes the octet. Let's do carbon dioxide. Take a moment and pause the video if you wish, and see if you can draw the Lewis structure for carbon dioxide. Here again, we draw the carbon has 4 valence electrons. Oxygen, like we saw above, has 6. And we can make a bond with each carbon right here. Forgot the 2 electrons right there. And now we can see that we can incorporate the lone electrons out here that are not bonded, and again these ones from the carbon right here, we can bring all of those electrons right here into the bonding region here and make a double bond on each side. So we can therefore draw the Lewis dot structure of CO2 as so, C with a double bond, and we remain with the lone pair electrons on the outside of each oxygen. So